Welcome to the subject operating systems, topic process synchronization. In the subject of operating systems, which begins usually with the idea called a resident monitor to take care of the common needs of many users of the same hardware resources, has now become many functionalities, 18 to 20 functionalities. The operating system's design, the operating system's internals, everything has become a very intricate study for many students at various levels, including undergrad engineering, postgrad engineering. Plenty of research is still to happen in this area of operating system. The technology is advancing to a point where today we keep telling the network is the computer. There is no reason to believe that all the resources that I want to use to solve a given problem using a program, using the application software, using the system software, using the hardware is done exactly on this machine and nowhere else. It can be done anywhere in the internet, anywhere it can be executed, the results can be brought, the physical resources can be anywhere. If there is a very expensive resource, we will connect to it and share it. Today we are talking about plenty of advances in the area of distributed systems, grid computing systems, cloud computing systems. We have thus made happen what is called a completely shared set of resources worldwide, which can be used 24/7. Now, what is the concern here? The concern here is either the user is expected to plan very diligently, very clearly, saying that this particular resource is necessary for solving this problem between this time to this time. We have had good experiences. We have been taking time off, let us say from 1 o'clock to 2 o'clock in some laboratory in Europe, and exactly at 1 o'clock the group of people who want to use the resources in that laboratory are expected to log in. So, there is plenty of preparation that goes behind. You have to get the users names, you have to get the users login IDs, and you have to give each user a correct facility. Exactly at 1 o'clock all the users will connect to a laboratory somewhere in Europe, which is permitted by the concerned authority which is physically holding the resources. They log in up exactly for 1 hour, 1 o'clock to 2 o'clock, they will have that computer laboratory working as though it is just their laboratory here, and we are logging in and getting our task done, but after 2 o'clock it will cut off. Whether there is a payment involved in it, whether it is only a mutual collaborative understanding or whatever it is, the idea proves to be very attractive because we do not have to replicate these resources. We simply do not have to replicate all these resources all over the world. They are necessary for a few people. These few people will purchase the computer time between 1 o'clock and 2 o'clock from anywhere, as long as they have a correct login and a correct password, good authentication mechanism, they should be able to use it. The idea is not new, it is very attractive. However, we need to understand that expecting all users to be that good in precisely planning their requirements on the computer needs is going to be more expensive than the computer time. The hardware costs have come down, the networking speeds are very high, the way in which we are connecting everything by fiber optic is proving every day that those will not be the constraints maybe next year. Next year they are no more the constraints. There is a fiber optic cable, high speed networking, good research is happening in all these areas. Networking capability of operating system is now on a very solid footing. So, then why do we want all users to rackle their brains? Please remember that there were days when saving 1 bit of the memory was a beautiful exercise. People were trying because there is a severe limitation on the main memory. Saving 1 microsecond of the execution time was a great achievement. The time efficiency, space efficiency, or what we call time complexity and space complexity, was a very challenging, intellectually stimulating exercise in optimizing the computer usage. Today we have relaxed on all that. Machines have become cheaper, processing has become very fast to a point where the user is very slow now. Processing is so fast that it is asking next second, the moment the user presses the carriage return, next second it is expecting the user to leapfrog into 3-4 steps. The user is at a lagging space and they have to catch up. So, the concern here is that they are over satisfied by the resources most of the time, and we are not using the complete resources. So, as a result, we have come to an understanding that please do not bother about too much of precision in asking for a resource exactly from this time to this time we want. There are certain cases like this studio. My good colleagues here in EM Square RC have ensured that this particular slot is available for me, nobody else is using. All resources are being used by 3 to 4 people, there is no contention, there is no way of clash, it is very clearly scheduled. But what do you do when things are not so physically visible, and how do we manage that? This is where the problem of critical section comes. We have plenty of resources, we do not want to multiply the resources. The problem manifests because of this. Lot of users need this resource, however exactly one process, one user can use the resource. This chair for example, exactly I can sit down in this particular point of time, not many people can do that. Such resources are what are called serially reusable resources. And when we talk about serially reusable resources, we have been saying that it becomes very obvious that let us say a shared telephone in a public call office, exactly one caller will be there in that booth. We have to find ways and means of making sure that exactly one caller is there in that shared public call office. There are so many such things which become very obvious, easy to understand if they are what are called serially reusable resources, the most simple form of a resource that makes it very obvious to all users that exactly one user program can use this resource. After that user program has exited from using the resource, somebody else can be scheduled. In this exercise, we have therefore found certain challenging problems of saying that there is a possibility that no process can get a resource, whereas everybody thinks that somebody else may be using it and keep quiet. The live lock situation, deadlock situation, there are so many such situations which become very clear if it is a serially reusable resource. However, if it is not so obvious like a serially reusable resource, what is happening is a very simple concern, saying let us say a bank account. We need to make sure that exactly once the bank account is updated by a particular transaction. Just because there is some concern in the network, some traffic in the network, you can't keep on updating the bank account at every whimsical time. Every transaction is happening exactly once. Thanks to this automatic bank accounting, we have understood the idea of a transaction. When one transaction is happening with your account, no other transaction is happening with the account. So, what did we do? In the world of databases, we called it atomic operation. That is, once the bank account is accessed, somebody is operating on that bank account to update, to change the data, nobody else is operating on that account. If that is not assured, it will be havoc. Any number of times, any number of people can read from that account the data pertaining to that account, but writing in is going to be exactly once. This is a kind of a critical section which is very clearly indicating that outside of what is obvious, namely serially reusable resource, the entire exercise in the critical section must be atomic. Nobody should disturb. If it is disturbed, we should have a way of checking that right at the step 1, we should have decided that it is a critical section, it should not have been disturbed. Now it is disturbed, we should have a rollback option. So, there are two varieties of resources. What is obvious is serially reusable resource which speaks for itself, like a chair, like a telephone in a public call office, exactly one fellow can use, no other explanation is needed, it makes sense. And what we have therefore done is we started using what was very famous as Peterson solution for serially reusable resource, saying that we need to simply make sure that there is a lock operation at the entrance, unlock operation at the exit. So, if I am modeling this chair in my program, I will lock the chair before I have sat on it, I will unlock the chair once I leave. This is how the process design will be there. The programmer is expected to tell precisely that it does not matter, whenever I get access to this resource called chair, only I will be using it. I am not too careful, my program is not so fascinatingly accurate to tell that it will be necessary between 1 o'clock and 2 o'clock. However, we have requested for a resource and there is a way in which the resource is allocated by the operating system. It is not my concern, but this particular problem is very challenging and it is called process synchronization. The user wrote a program, the program has gone into execution. Roughly speaking, the user program, in whatever be the language the user has written, when it goes into execution mode, is called a process. This process has shared resources, and these shared resources can be of two types. One is serially reusable, others are those where atomicity must be ensured. Once the resource is accessed, until it is released, nobody is going to disturb this process in execution. If it is disturbed, we should have a rollback. We should know where is the safe position to undo the damage, possible damage caused, and then progress. These are all some simple ideas. For so many times we have had these concerns. We go to the ATM, the ATM simply refused, or it says it has debited but cash has not come. Somewhere in the process the error has happened. It has got the permission to issue the money, but money did not come. So, what is it that was called? These were the days when there was no reverse operation. The reverse transaction was not there in many ATMs. You have to simply go to the bank, report to them saying that it has said yes, the transaction has been approved, so much of money must have been deducted, but then somewhere after that decision has been taken by the system, it failed. And now it says it is not able to transact. So, we have to go back to the bank, tell that, see, from so and so particular ATM, I have withdrawn this. Gradually the technology progressed, the machines progressed. We found in the initial days this may be safer because the bank is aware, saying that virtual debit has happened. People were fighting, saying that one day what will happen to the interest? Virtual debit has happened, my bank account is showing a lesser balance for one day, and then you will be penalizing so many times. Every technology has its own concerns. Every new shoe pinches. We have learnt how to improve the systems. The more they have, the more. In the beginning, nobody wanted the ATM. Once the ATM has come, gradually we are getting used to that solution. We are now becoming dependent. Everybody says drawing money has nothing to do with the bank now. It is only to find a place where the ATM is there, accepting the card. Money transactions which are there somewhere, it has nothing to do with the banking, and the banking people are on the defensive. They do not know why, they do not know the customers outside of what is happening in the machine. So, these are all the concerns which we will have to understand. The social systems, the computing systems. Peterson's solution is a very simple solution. What he said was very simple. He said, let there be a lock at the beginning. For serially reusable resources, we understand this. Whereas for the other resources like a bank account where atomicity has to be ensured, we have difficulties, because if it is broken, you should have a rollback mechanism, like I said, reverse transaction. It has not happened, it will simply be reflected back in few minutes, it will come back, few seconds, it will come back saying that it has not been withdrawn, you are back with the balance. That is a better solution, but then machines have to improve, systems have to improve, people have to understand what is happening, then it will settle. Synchronization hardware, there are ways and means. Banking procedures are more rigid, so they have ways and means of making sure, but they may not tell in as many terms, but practically the banking procedures have evolved over so many decades, we trust them. The bank has built a trust, it goes. We are not penalized even by 0.0001 naya paise in the entire set of transactions on the book. However, what we need to understand is, once we started automating certain transactions, we have seen the improvement in the quality of service, quality of life. Today we are not concerned about the working hours of the bank. We just want to find out where is the ATM, where the card can be used, internet banking, so many things can happen. The facilities have improved, railway tickets, cinema tickets, everything follows the same rule. Some transactions must be atomic. There is no second opinion about it. How to implement these atomic operations? There are three levels of implementing the atomic operation. One is at the hardware level. See, the very early days, of computing, we had a very specific chip which had all these mechanisms. They were called spin lock mechanisms. We had the Motorola chip, which was giving a hardware support in anticipation of certain requirements, saying that the lock is physical, you go lock it inside, do the critical section exercise, come out wherever the resource is. The Motorola chip was so advanced by design at that time that they never thought, why is this spin lock mechanism, why should I have a hardware lock feature? It's becoming very expensive. They are showing it as a special functionality, it's costing more than the competitor Intel because of this facility. Since there were no application there are so many such ideas in computer science where, because there was no serious application, nobody bothered about it. It includes the now the most famous object oriented analysis and design. For 4 long decades nobody knew what exactly to do with this new idea of technology. After 4 decades it picked up, and it picked up pace frantically, and all of a sudden we could not produce so many people who are aware of this object oriented analysis and design and how it happens. Things have improved, we have better people. 2 decades it took for people to stabilize on many things. Semaphores, this is the way in which we talked about at the operating system level. There is no need to think that process synchronization must be supported only by the operating system. If you want to be very serious, we should have a support at the hardware level, we should have a support at the software operating system level, we should also have a support at the application programmer level. We will talk about it as we progress, but how do you know that your solution is working? There are certain theoretical problems which you can apply the solution on. As we moved further into the programming space, we started talking about regions, we started talking about monitors, and then we started using them on synchronization examples. So we have to have solutions at 3 levels if you want to be absolutely sure of solving the critical section problem. 1 or 2 preliminary ways of checking may be enough for certain simple examples, but then if you really want to be sure, you should have 3 level checks, and that is when the transaction is supposed to be atomic. To introduce the critical section problem, whose solutions can be used to ensure the consistency of shared data. Data particularly gives a lot of problem because atomicity is demanded by shared data. If somebody is working updating that data, atomicity is, they demand atomic operations. To present both software and hardware solutions of the critical section, to introduce the concept of an atomic transaction. Concurrent access to shared data may result in data inconsistency. One fellow is updating, one fellow is removing. What will you do? Which one happened first, which one happened later? These are the concerns. Particularly when it is monetary transactions, we should be even more clear. We have built a very robust system which works very well with many paper based rules and regulations, and we are very confident that it works. It's just a case of making sure that the user is not put to undue stress. That is all is the concern. It is not fair for any technology designer to put the user in undue stress. New shoe pinches, all right, but then it cannot cost a leg. That's all is the question. We make a new shoe, but we should be careful. Suppose that we wanted to provide a solution to the consumer producer problem that fills all the buffers. We can do so by having, and this is one very popular problem, consumer producer problem. The point is, there is a producer that is giving certain things and the consumer is asking, what happens if the demand is so high that the producer is choked, they are not able to produce? How do you check whether it has happened or not happened or it will happen? All of us will think that it's only matter of time. Next 10 hours the producer will produce some more time, we will wait. How do you know it is producing? Problems are there. Like that we have some theoretical problems based on which you can check out your solution. So, this is what is the case. The producer is producing, putting into a buffer. It can produce only items that can fill the buffer. If it is buffer is full, even the producer is producing, but the buffer is not accepting, it is overthrowing, it is saying that no, buffer size has exceeded. How do you know it has occurred? We are all very bad as programmers when it comes to anything to do with memory which is dynamic like this. Anything that is to do with dynamic memory management requires a lot of experience of programming. We simply tell that 10 years you become a good programmer. Please do read this paper by Peter Norvig, 10 years to teach programming. 10 years to learn programming is the exact title. I am not quoting the title exactly, but do read that paper. It is very good. It takes 10 years to become a programmer, nothing less than 10 years. And after 10 years, there are still certain programming challenges like dynamic programming, dynamic memory management. They are still baffling some of the best programming brains. We still say that 1 out of 7 lines is defective. Our engineering discipline is slightly different in that sense. We are not likely to compare this engineering discipline to other engineering disciplines which cannot afford to tell that 99.9999% is our reliability. That is still not acceptable. 100% reliability, whereas here we are not able to get any beyond 33 to 36%, but whenever it works, it's a phenomenal impact on a large population. The quality of life has improved, the quality of services have improved. All the more reason why the new challenges in software engineering are ahead. We have to face more challenges ahead. There is a race condition. The race condition is understandable. There is a resource. At this point in time, the resource is declared available. Suddenly the operating system says, yes, the resource is available. 20 people are rushing to get that resource. At the same time, maybe same timestamp, something should be there to serialize that this came first, this came second. It should not only be fair, but it should also appear fair. There is a fairness criteria. The race condition is so dominant in the way we are thinking that the producer is producing, the consumer is taking, the consumer is racing, the producer is not able to produce, the producer is able to produce lot more and the consumer is sleeping. The buffer is getting full, items are being thrown out, but nobody is bothered. Such conditions, however theoretical they may sound, are very, very serious. And whenever we are telling that a solution for process synchronization has been mooted, all these checks have to be implemented. Mutual exclusion, exactly one process is using what we called that resource, which is becoming a critical. Until then it is a resource like any other resource, but the multiple processes competing, and this resource is of two types. One is data which demands atomicity, the other one is serially reusable resource. In either cases, mutual exclusion, exactly one process is executing the critical sections. The operations of a process on an existing resource which should be serialized, which should be assured that only one process is doing, that is the problem of critical section, which we should understand carefully. If no process is executing in its critical section, there exists some process that wish to enter the critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. This is an error in system design which is so obvious. The resource is free, as I said, the live lock condition, nobody is granted resource. We have utilized this much later. Today we are talking about denial of service, distributed denial of service. Everything is there, but the service is not happening. It can happen. We have to think very carefully about the systems design. Bounded waiting, we should know that there should be a bound, upper bound on the number of times the request can fail, the upper bound on number of times the critical section can be used. We should take turns. If you are going ahead with the reservation of a resource, if you have not utilized that reservation time, you should come back and stand in the queue. Otherwise, what will happen? You are disrupting the entire scheduler. People who are waiting behind, you have the particular process, the one that you have given which is late. So, what we have done is we have made sure that the software controls in the name of synchronization which will work in tandem with the hardware supports, software at both levels, systems, operating systems level, application programming level, to make sure that all these nice things have been properly implemented. One of the finest solutions is due to Peterson. Peterson said, let there be two instructions, load and store instructions, that are atomic. They cannot be interrupted, and you use them, saying that in the beginning we will use the load instruction, in the end you will use the store instruction. The load is getting the data into the memory variable, store is putting it back. Until the load and store instructions are completed, nothing can interrupt them. And if it is interrupted, we will go back all the way before the load instruction has been executed and roll back everything. It is as though nothing has happened to that data. The system ensures Peterson's solution is like that, and it is something which is very, very interesting. In a simple way, we have included that this is how it is. The critical section will ensure that the load and store instructions manage the critical section with due atomicity by using just that flag. For every shared data item or for every resource which is demanding an atomic transaction, there will exist a flag. Every flag is there for I, whichever is the resource where it is demanding atomicity, there is a flag, and once the flag is up and down, the load and store instructions are operational. In a very simple way, Peterson has told us that it's practically possible. In the software, it is possible. In the hardware, many systems provide hardware support now. In the beginning, the Motorola chip that was far-sighted to make that happen was not so economical in design, and people were thinking that this set of features are not usable right now. Maybe after 10 years we will use, after 15 years, but until then the model should be in the current business. So therefore, what they have been doing, they are moving away for other processes, but it's a very good idea, very good hardware support. Uniprocessors could disable interrupts. Currently running code would execute without preemption. So the market dynamics are well appreciated. That's a concern that we have most of the time. It is not that one technology is outdating other technology, another technology is killing another technology. That is too naive a viewpoint. The market dynamics are regulated. We have so many regulatory frameworks. So a healthy competition, both in terms of aggressive implementation of the features, aggressive marketing, all these things are ensuring that we have a way of managing what is exactly needed, be it on price basis, be it on feature basis. We think that the system is actually fair. Generally, two inefficient or multiprocessor systems, today a single chip is having many CPUs, multi-core architectures are very common. Atomic simply means non-interruptible. Actually, when we talk about atomic instructions, it is not merely non-interruptible, but when an interrupt happens accidentally which we didn't plan, it also tells what to do, for how much of the exercise you have to roll back and restart. It is a case where we have been talking about in many ways that rollback option is necessary in data. Today we have all that. For example, many years back we didn't have the reverse transaction in many ATMs, at least on Indian soil. Other ATMs might have been provided, they have been upgrading, in the software. Machines may not be upgradable overnight, hardware is not so easy, software is very flexible. We have understood how to reverse the transaction. 1 second it comes, it's an erroneous transaction, next second you get a message saying that no, it's not yours, don't worry about it, it has been repatriated. Either test memory word or set value or swap contents. Essentially, we have been talking about a way of creating, before critical section you should acquire what is roughly equal to a lock, whatever way you call it. After the critical section you should know how to release the lock. This will take care of serially reusable resources any number of times. It will also take care of the necessity for atomic. Atomic does not mean only this. Atomic means it should also tell precisely what to do when this mechanism fails and you have to roll back. Solution to critical section problem using locks became very famous. Different instructions, different manufacturers have created different instructions, different operating systems support the different terminology. Test and set instruction is one support which a system gives. there is a test there is a test, and then there is a way in which we have a set instruction. One is done before the critical section, the other one is done after the critical section. So, the operations performed on a shared resource is what is to be ensured as a critical section operation. We had swap instructions, multiple instructions are there, bounded waiting. How do you know that in this process the waiting time is not more than this much? We have a theoretical proof. We have those conceptual problems like bounded buffer problem, readers writer problem, sleeping barber problem, dining philosopher's problem. If whatever solution you have proposed as this is how I will manage the critical section, if it is solving these problems, it is very likely to work in the real context as it worked on the theoretical problems. There was a point in time when it was a very ripe research area. We have seen what is the solution at the hardware level, we have seen what is the solution at the software level. Now we have to see, is there a solution at the language level? The answer is yes. There have been several languages which were supporting what is called a region construct. Region is defined as a critical region. You define what is the region, automatically the compiler will boil it down to what is the support that the operating system is providing, what is the support which the hardware is providing. It is the job of the system software, it is the job of the compiler, it is the job of the hardware designer to make sure that this region construct which is specified so well by the programmer is implemented in a manner where it should be implemented. So, at a higher level we got region constructs. There are plenty of work has happened. Today, as I said, we have multi-core chips, not one processor, multi-cores are there. We talked about parallel processing, we talked about concurrency control, synchronization today, process synchronization today is a very important aspect, and everybody should know, every student of operating system should know that there are solutions like this at the hardware level, at the operating system level, at the language, and therefore the application programming level. The region construct is too small in granularity, it just specifies this region and presumes that the operating system is working correctly, hardware is working correctly. Two levels of support it is demanding, and it presumes that it is working. What happens if it is not working? So, what we did was, the programmer should not be woken up very rudely saying that the region construct is fine, the language is working finely, but then the operating system support is not there. All of a sudden there is a vacuum, all of a sudden there is a hardware. That kind of a wake up call to the programmer or later on to the user. If the programmer is waking up, it is easy because he has a solution, he has been thinking about the problem. Poor user, what will he do? He will be at a loss, he or she will be at a complete loss because everything that has been presumed has failed. We still have such possibilities that it has passed the hardware filter, hardware check, passed the system software check, passed the programmer's check, compiler, system software, so much. At the time when the user is using, that condition we did not expect. It was not expected, that is a dynamic condition. We thought adequately to imagine what are all the possibilities. We cannot enumerate all infinite possibilities. Whatever we have anticipated, we have programmed. This is unanticipated. What is the cost of that unanticipated error? It may be lot, because today software is impacting lives. Physically people are dependent on software. So, we have been telling that we should become more and more experts on the way in which we are writing the software. Semaphores are there, general synchronization tool, a binary or a counting semaphore. Semaphore implementation is at the operating system level. We talk about a semaphore, P operation before the critical section, V operation. Everywhere, whenever there is a critical section, one operation happens before the critical section, another operation happens after the critical section, and this method is so popular, and we attribute it to Peterson in a very nice manner, that it is possible at the hardware level, it is possible at the system software level, it is possible at the application software level, it is there in the language now either as a simple region or a monitor. We have to have two operations, block, wake up. The idea is very simple, but however, we need to make sure that there is no live lock. The resource is there, nobody is using. There is deadlock, appears to be something happening, nothing is happening. Deadlock situation, there is a topic called deadlocks later in the set of lectures which I have given. Starvation, that is one fellow is indefinitely waiting, it is wrong design. Priority inversion, we should have prioritization, we should have a way of scheduling when multiple people are rushing. Once the resource is free, they are all waiting for the resource to be free, once it is free they are rushing. These are certain classical problems of synchronization. You can read it up in the textbook. Theoretically, if it solves these problems, bounded buffer, limited buffer, producer is producing, consumer is producing, one fellow should not choke the other fellow. Readers, writers, many readers can happen, only one should write the data, bank data. Dining philosophers problem, all philosophers are round the table. This is what we have been telling, only if a philosopher gets both the forks he can eat, but only one fork is readily available, he has to wait for the other fork. These are theoretical classical problems. At the language level, region, monitor, a schematic view of monitor, it is much more sophisticated than the region. Even if everything fails, it will work, monitor will take care. So, these are the ways in which we are solving the synchronization problem in operating systems like Solaris, Windows XP, Linux, pthreads. What we need to ensure all this is happening, a system model, log based recovery, very simple method, we look at the log and find out, checkpointing, concurrent automatic transactions. That is all is necessary. Thank you.